My name is Emma Norman. I'm in a remote sensing class offered at the University of Maryland by Dr. Steve Mitchell. Students went out to different sites on UMD's campus with field deployable Lidar sensors to map their object of choice and generate a 3D point cloud from their data. In this video, I'll talk about remote sensing concepts, my Lidar instrument, data collection, and data processing with software tools.
Remote sensing is the collection of information about an object without making physical contact with it. Some common examples are sonar, radar, and Lidar. With Lidar, this is done by shooting photons from a laser at a target and then collecting them after they've reflected off of it. From this, an observer can get data about the distance and geometry of an object. A Lidar instrument also needs a control system to run data acquisition smoothly. In my Lidar instrument from this course, a line laser is the transmitter and a Raspberry Pi camera is the receiver. The entire system is controlled by a Raspberry Pi. The Lidar equation models the considerations that contribute to the data the receiver collects. These considerations are the strength of the transmitting laser, how the target surface reflects or scatters light, the surface area receiving photons, the distance of the instrument from the target, the transmission coefficients, instrument efficiency, and the amount of ambient light creating noise are all factors that contribute to what the receiver sees. My target to map on campus was the Reckord Armory Cannon. It's located by Route 1 and the front entrance of the Reckord Armory. It's about 5 feet long, 3.5 feet tall, and 2.5 feet wide, so it's a moderately sized object. I chose this object because I walked past it on the way to intramural sports games, so it has a little bit of sentimental value to me. Also, I thought the geometry was interesting. I thought the cylindrical tube of the cannon would show up well in my scans, in addition to the ball on the end and the two flat shields on the sides. I thought that the front mouth of the cannon, where there's a hole going in, would be a unique feature to map, and I was interested to see how that turned out. This is a Lidar instrument used to take data at my target on campus. At the top, you can see a blue Ethernet cable. This connects to my computer in order to establish a VNC connection into the Raspberry Pi. The Raspberry Pi is connected to our Raspberry Pi camera that acts as a receiver to the system. So it takes a picture of the target while the laser is shining on it. Speaking of the laser, this can be found exactly 12 inches away from the Raspberry Pi camera at the bottom of the instrument. This is the transmitter. It transmits a red line laser onto the target that then bounces back to the camera receiver. The line laser is powered by an Arduino Uno. The Arduino Uno in turn is then powered by the Raspberry Pi. So an Arduino Uno is used instead of a battery pack in terms of future scalability. So an IMU chip could be used to measure the angle of the LiDAR sensor as it tilted vertically. However, this instrument uses a cell phone application. The cell phone is mounted to the back of the LiDAR mount and uses an application called bubble level in order to read off the angle. The LiDAR mount is fixed directly to a camera tripod with a bolt, and it's tilted forwards and backwards with the handle of this camera tripod. So that's how we change the angle of the LiDAR mount in order to map different geometries of the target and take pictures at different angles, again, with the Raspberry Pi camera. The last feature that we haven't mentioned is the battery pack. It's also attached to the back of the LiDAR instrument mount right above the phone that we're using to measure the angle. The battery pack powers the Raspberry Pi directly, and then it's the Raspberry Pi that is providing power to the rest of the subsystems. This Raspberry Pi runs Python scripts that use the OpenCV library. After I take pictures of my target, I'll need to isolate the red laser light in my images to effectively process my data. Essentially, I need my data processing script to only look at the laser light reflected back from my target and not at any light coming from ambient sources, since any other light that doesn't come from the laser will generate noise when I'm trying to create a 3D point cloud. To prepare for data collection, I tested applying an HSV color mask to clips I took at home. In this example, I'm testing a green HSV mask first on a picture and then on a video of a point laser. The HSV mask is different in changing lighting conditions, so I spent some time playing around with values in order to find the ones that filtered out the right amount of light. I had to redo this if I took pictures from different angles or inside versus outside. In order to calibrate the camera in my Lidar instrument, I took pictures of my line laser shining on a flat wall. Each image was taken 6 inches apart, starting 1 foot from the wall until 10 feet away from the wall. I ran these images through a laser alignment script that applied an HSV mask and then plotted a laser calibration curve as a function of the distance from the wall and the number of pixels illuminated by the line laser. The first time I ran the script, my data points did not match up with the expected calibration curve. To fix this, I changed the gain, RPC, and the radian offset, R0. The radian offset compensates for laser alignment errors. My first Raspberry Pi camera actually broke part of the way through the project, so I needed to recalibrate my instrument, but because my line laser was already glued into the mount when I was attaching my replacement camera, the camera and the laser were not perfectly aligned, and my radian offset changed quite a bit. However, after changing my R0 and RPC values, I did come out with a pretty smooth laser calibration curve. You can see that my data points do match up well with the expected curve, so after that, I was ready to go outside and start mapping my target.
I went out to map the cannon at night. It's in a very dark location, so it's a little hard to take video representing what I'm doing. But you can see here the LiDAR system is set up and the laser is on. However, it's very hard for this camera to pick up on the cannon surface. It's also hard for the Raspberry Pi's camera to pick up on the surface, is what we found. So while taking data images, the black surface of the cannon absorbed a lot of the light instead of reflecting it back to the Raspberry Pi camera, and that brought up issues with getting clean data to process later. Another issue that we ran into were street lights in the area, so it is very dark right by the cannon, but in the background of some images, there's a red stoplight, which caused some problems with the color picker, and also ambient street lights that just kind of saturated the camera's frame, and that messed up the data a little bit. So we took a few steps to remedy this. I put a sheet over the tree that is hanging next to the cannon in order to block the street light and cast a shadow over the cannon. I also wrapped the cannon in the sheet in order to create a more matte surface. So it really was a step-by-step progression of adapting the situation in order to get good data. And also to get good data, I use a long exposure code, so the aperture stayed open for 2 seconds as opposed to what the default was, whatever that might be based on the light levels, and the longer exposure code allowed the camera to pick up more of the red line laser than it did without it.
After taking images with my Raspberry Pi on different sides of my target and moving them to my computer, I can use Python script data generation.py to generate a text file of point cloud data. So here I have the left side mapping of my Canon folder with different images. So here you can see the image is pretty dark, but the red light of the laser clearly shows up. Again, this is the left side of the cannon. So in data generation.py, we have the HSV mask that we talked about earlier, the R0 and RPC values that we were looking at earlier, and we are importing all of the images from the left side folder and generating a text file into the same folder. So we're just going to run this and see what our output file is, because we will be aligning it then with XYZ data from the other sides that we've mapped and then processed. So here you can see datageneration.py as output a plot of the point data that the script just generated. It doesn't look much like a Canon yet, but as we move it into Cloud Compare to combine it with data taken from other angles, you will see that it starts to resemble the target more closely. So I've imported 4 different data files into Cloud Compare in order to combine them into one object. The back, front, left, and right orientations. When you first put them into Cloud Compare, they don't look like a whole lot. They're not correctly oriented and they're not overlapping. This is due to where the Lidar instrument was located during mapping. It's not in the same spot in order to reach every angle. You can see there's also some extraneous data points way far out. These need to be trimmed off. They're largely due to ambient noise, such as the street light nearby, or there's also a traffic light in the back of some of my scans. After processing, you can see that the data points are much better aligned. It's one cohesive cloud. You can really tell that this is the target, the cannon. You can see the body of the cannon barrel, as well as the front, the shields, and the ball at the end of the cannon. After exporting the combined 3D point cloud from Cloud Compare, I've imported it into MeshLab in order to create a 3D mesh of the surface. So essentially knitting all of the points together to create a flat surface. In order to do this, we first compute normals for point sets. We bump up the neighboring numbers. This is done by trial and error in order to find a setting that has all of the normal vectors coming straight out of the body of the cannon. The next step is surface reconstruction. The algorithm I use for this is ball pivoting. I changed the values of the ballpoint radius and determined the value I wanted through trial and error in order to create the most connected surface mesh that I could. As you can see, even my final mesh is not completely connected. Some things that could fix this are a denser point cloud so that the mesh algorithm has an easier time connecting the points. Additionally, another map from the underside of the cannon would help fill in data from the bottom. I couldn't get my Lidar instrument low enough to take data from this angle, so there's not point cloud data at that point, and therefore it made it really hard for the mesh algorithm to recreate the smooth surface on the underside of the cannon. Overall, I'm pretty satisfied with my data. Many of the features I was looking to map did indeed show up: the curved surface, the ball at the end, and the shields on the side. After finishing, I removed the normal vectors shown on the point cloud in order to show the smooth final product. Thank you for listening, and I'd like to give special thanks to Professor Steve Mitchell and TA Will Bogdan for their help with this project.